Okay, so next we have a invited talk from Tom Rainforth about inference trees. So Tom Rainforth is a postdoctoral researcher in the Department of Statistics at the University of Oxford in EY Taste Group, and he has done a lot of interesting work in the interest of this workshop, including the ones that kind of motivate the previous talk about the signal-to-noise ratio. So, but today he's going to talk about some more recent work, and looking forward to it. And looks like we have some problems with connection. So actually for the speakers in the following sessions, can you just please, in case, also send your slides to a friend in advance, like just in case the laptop does not connect.
Is there Wi-Fi for to do that with?
I think there's Wi-Fi. While they're preparing, I'm making an announcement. For the second session of the post session, could you please also take off the poster, I guess, during the lunch break, and also the authors for the second post session, could you please also put up your poster before the afternoon session starts?
Done previous years. There's so much energy.
I guess you enjoyed some satisfaction. What's the connection like? I think it's what if I serve it. I don't see a connection.
Also, I guess there's also
Okay.
Sorry about the delay. Can everyone hear me? Great. So Yeah, so after the delay, the paper is called Inference Trees, Adaptive Inference with Exploration. And it's a joint work with Yuan Zhao, Xiaoyu Liu, Yiwei Tei, Frank Wood, Hansu Yang, and Jan-Willem van der Meet. So what we're going to introduce is a completely new class of inference algorithms. But one of the key ideas we're going to be trying to convey is that adaptive inference methods need to explore, not just exploit. What I mean by that is that most adaptive inference methods are inherently greedy. They presume that their samples so far are representative of the posterior, and they always use the best proposal they've got at every iteration. They don't have any notion that they might be wrong, and they need to explore the space to find regions that they may have missed. So what it's really doing here is it's failing to recognize that the utility from those samples is generated not just by their combinations of the estimator, but also because they're going to inform the future adaptation. And that future adaptation needs direct control for exploration. Hopefully, once I've convinced you that that's a good idea, I'll start going into the inference tree algorithm itself. So, as I said, inference trees are a new class of inference algorithms. They're loosely based around Monte Carlo tree search, and they're going to look to explicitly balance this exploration and exploitation. At a very high level, what they're going to do is they're going to take a base inference algorithm like importance sampling, they're going to chop it up into lots of different regions, and then they're going to use a meta controller to control how to run the inference in each of those regions and then stitch it back together again. Key to being able to do this is going to be a separate novel scheme for doing some targeted exploration. We don't just want to sample everywhere uniformly, we want to know where to sample. If we start to think we're uncovering a mode, we need to sort of hone down on that region and really focus where we're exploring. To do this, we're going to do some clever things with the log weights. So we're going to look at the density of the log weights. We're going to use that to predict subjectively where we think we might have to look. Okay, so we're going to take a relatively standard setting. We'll have some target distribution pi of x, typically the posterior. We have access to the unnormalized form gamma of x, and we have some unknown normalization constant omega. So if we think about what's wrong with that adaptive inference, let's look at the importance sampling setting. So here we have some unnormalized target gamma. We're going to start with some proposal qt of x. We draw samples from qt of x, and then we weight them according to the ratio of gamma to q. And so here we have in orange these set of weighted samples, and that's an approximation of the posterior. So what we're doing is we're saying, well, we've got information in these samples. We want to use that information to improve the future sampling, to update the proposal. The classic way of doing this is going to be to minimize the KL divergence between the empirical measure of those samples and the proposal we're going to use. So we're going to choose the proposal that best fits those samples. So in this case, it'll give us the new proposal in black. And we see that new proposal in black quite nicely matches the target distribution. Except it doesn't. Actually, there was a big region we missed. And in fact, we never sampled in anywhere near this other mode, and we just greedily collapsed down to one of them. We failed to account for the fact that actually our samples might not be representative of the posterior. And this is quite a silly assumption to make, because we're doing adaptation because we haven't got a good proposal. So it stands to reason we probably haven't got a good posterior approximation already, and we need this exploration. We need to think about where can we update things. So what we really want to be doing is looking at an exploration-exploitation trade-off. We successfully did the exploitation. We did sample in regions where we thought the posterior mass was high. What we didn't do was we didn't explore in regions where the uncertainty was high. We didn't realize we need to search these regions, we need to find information, and we need to explicitly make that information important. We forgot that this utility of those samples is not just their contribution to the final estimator. So how can we actually think about balancing this exploration and exploitation? Let's imagine we've just got some bounded posterior like this. It happens to have two modes. One thing we might think of doing is chopping it up. We can insert these two partitions. This is going to give us these three separate regions. And then we can consider these guys as separate inference problems. So if we started with, say, an important sampling proposal for the full region, we could truncate that proposal to each region, form their own posterior estimate for each, and then stitch them back together as a stratified sampling. The reason we might want to do this is we can then allocate resources to these. We've created something that looks quite like a bandit problem, and now we can consider how can we balance exploration and exploitation by how many resources we're going to give to each of these regions. But why didn't I just do that in one proposal? Why didn't I just learn a proposal that could balance these both at the same time? Well, basically, we're breaking the IID sampling framework, and that's going to bring a lot of advantages. we're going to give a lot more explicit control on where we can give samples. So we've got a separate estimate for our posterior and what we're actually using. And we can do things like, say we find a new mode, we can concentrate all our sampling on that new mode rather than the one we've already searched. So breaking SciID framework is going to be very helpful. The other thing it's going to let us do is actually gather information more effectively. So this is going to be quite difficult to see in the importance sampling setting, but when we come to doing the sequential Monte Carlo, it's going to be essential. Here we're going to be able to forcefully return information in areas, and it's going to make sure we gather the information we need to do the future adaptation. From a more technical perspective, it's also going to make proving consistency really, really easy, which is great because usually it's notoriously difficult to prove that adaptive samplers converge because of the pathologies I was showing at the start. Okay, let's get down to the actual inference tree algorithm itself a bit more. So as I said, it's going to work like a meta algorithm. We're going to start with some base inference algorithm. So you could think about maybe having important sampling. We start with some proposal. And what we're going to do is we're going to chop the space up into, separate regions and then control things. So here we've got this tree. The root of that tree is the full space. Then we have a partitioning shown in blue, which is giving us these two new sections. Then we hierarchically, through this binary splitting, have the space where each node is a region of the space. For each of those regions, we can run a local inference. We can kind of truncate our proposal and run inference on that region locally. And so what we're going to be doing is we're going to learn this tree and use it at the same time to allocate our resources. To do that, we'll go through like 3 key steps. The first of these is a traversal. So we've already run inference a bit. We have information at each of these nodes. And that information is going to tell us what we need to know about where we should allocate our resources. So what we'll do is we'll start at the root node, and then we'll recursively choose one of the 2 children. Do we want to go left, do we want to go right? So here we start at the root node 0, we choose node 2, then we choose node 4, and so we end up in the leaf node 4. Once we're there, we want to refine our estimate at that node. So remembering that we want to learn this tree as we go, we're not just going to run more inference there, we're also going to update the tree. So in this case, we're going to take node 4, we're going to split it into 2 nodes, 5 and 6, by choosing a careful split based on the samples already there. And then we can run inference on each of these new nodes and update things. That update is a propagation step. So once we've run inference at each of our 2 new nodes, we need to update all of its parents. So the combination of nodes 5 and 6 was the space for node 4, so we also update node 4, then we update node 2, and we propagate through. So we have these 3 steps. We traverse down the tree to allocate our resources, we refine the estimate in that region, and then we propagate the information back up to improve the future strategy. Okay, so let's go through these in detail, and let's start with the propagation. So it turns out the propagation is basically just online updates of the inference tree estimator. Again, it's going to be easiest to think in terms of importance sampling. So we've got a marginal-like estimate I'll call omega hat j, and that's just the average of the weights at that node if it's a leaf node. So it's standard importance sampling marginal-like estimate. If I'm an internal node, though, I have 2 estimates. I have one estimate from when I was a leaf node. Because we're growing the tree, every node was once a leaf, and those samples remain around. The other thing we have is 2 estimates from each of the children. So we have an estimate from the left child, omega hat L, and then we have omega hat R. They're a stratified sampling thing, so the combination of those 2 regions is the full space, the sum of their estimates is the estimate for the full region. Now we've got 2 estimates for the same thing, and we need to combine them. So we'll take a convex combination, and we'll introduce some factor Cj. It's a kind of child preference factor. How much weight do we give to the child's estimate compared to our own estimate? So over time, we'll take more samples of the child relative to the parent, and Cj will increase towards 1. We're also going to propagate an unnormalized target measure approximation. We'll call that gamma hat. That'll go up in the same way. We'll just have a weighted set of unnormalized samples, and also the estimates from the children, and we'll propagate that in the same way for this child preference. Only once we get to the root node are we going to self-normalize. So we're separately propagating up these marginal likelihood and these unnormalized things, and then when we get to the node, we get to self-normalize. I won't get into too much detail about that, except to say it's critical to the convergence. And that convergence is very nice. It says, basically, regardless of how we actually adapt, we get convergence as long as we satisfy some very weak assumptions, which is basically that the base inference algorithm is itself consistent and that we make sure we don't miss areas completely. And this is really useful because it means we can have freedom to sort of adapt the algorithm practically in these other things without worrying about the convergence. But of course, these other terms are going to be very important to how things work out practically. So let's first think about how we'd actually want to allocate resources if we knew everything. So if we've got an oracle and that oracle knows all the real information, how would you allocate resources? And it's so interesting because it turns out you actually don't want to sample in proportion to the posteriors. Because it's a stratified sampling setting, not an important sampling setting, the standard deviation of the weights is also important, not just the expected weight, which is the marginal likelihood. So you can think about this way. If I have two nodes with the same marginal likelihood, where the first one has a good proposal and the second one has a bad proposal, I need to sample more from the one with a bad proposal to make up for the fact it's got a good proposal. And so I need to incorporate both of these terms asymptotically to do the most optimal thing. So here we have more precisely, the optimal thing always takes this form, where we firstly have the marginal likelihood squared, plus some factor times the variance of the weights, where this factor is critically at least 1. So this is kind of a smoothness parameter, where if it goes to 0, it's the sort of standard Monte Carlo assumption that there's no correlations anywhere. As it goes to infinity, it becomes the best thing for doing the marginal likelihoods. And so we usually take it as just 1, but we need to care about both of these. Okay, now we know what we want to do if we knew everything. Let's think about how we can actually allocate resources when we don't. And that's basically the traversal strategy. Given a tree, where do we want to update? As I said before, we're going to start the root node. We're going to recursively choose a left or a right child until we hit a leaf node. And so we can think about the traversal strategy as just being a problem of which child should I take of the two. And so for this, we can build on the bandit literature. In particular, upper confidence banding for stratified sampling. So here we choose at each iteration, we're going to choose the child with the higher utility, where the utility is defined as follows. So we have at the front one over the number of times we've chosen it before. So we're going to, if we've chosen an arm more often before, we want to choose it less in the future. And then we have two terms in here. We have an estimated reward. I'll come back to what that reward actually is later. And we have what's known as an optimism boost. This optimism boost is the typical way of getting exploration. It kind of says, the more we've had this problem, we haven't chosen this arm, the more we need to choose it. So it's kind of a minimum number of choices we have to take per arm. And the problem with that is that it only gives us a uniform exploration. It just says, you have to make sure you do everything enough. It doesn't really tell us where we should be doing it. Where is our uncertainty is actually high. So instead of doing the naive thing of taking our reward to just be what we thought before we should asymptotically sample in front of it, we should also take two terms. We should take an exploitation term and a targeted exploration. So the exploitation is what we want to sample from asymptotically. So as our estimates become perfect, this is how we want to sample. This is the theoretically optimal way of doing things. But we can't estimate that very well often, and so we need to think carefully about the fact that our estimates are not perfect and we need to target where to go. So we also need to do a bit of a change to make sure these guys scale the same size. So we're going to scale them by their parents' estimates. And so we have these two terms to dictate the two things, and this factor delta that controls how much we care about each. So at the start, we're going to mostly look at exploration, but over time, we'll move to be more and more exploitative. But how can we do this target exploration? What term can we use here that's actually going to help us see where we need to look? Well, what we're going to do here is we're going to look at the log weights. So the weights are usually almost all 0, except one is very high. They're really difficult to look at. There's not much information there. If we look at the log weights, there's a much more well-behaved distribution, even if our samples are terrible. So here we've got on the x-axis log weights, and we're varying over thousands. So we're varying thousands of orders of magnitude here. We have a really, really terrible sampler. But we still see that the distribution of these log weights is okay. So in blue we have the left child, and in red we have the right child. And these are 8 samples where, in this case, it's one of the experiments we have later, we run SMC, and these are the marginal likelihood estimates. And so, because there's such a big variation here, the Monte Carlo estimate is basically the maximum of these samples. The other samples really do not contribute in any way at all. But they do contribute information, significant information, because they tell us how likely it is that we might get different things. So we could think about, for example, putting a kernel density estimator with these. We could reason directly about the distribution of the log weights. And we could say, in a sort of frequency sense, if they were generated from this, how likely is it if I keep running this that I'm going to start generating samples at a different thing? And the question we might ask in particular is the marginal likelihood for that region greater than some threshold of interest? So that threshold might be sort of the current marginal likelihood estimate minus some sort of scaling. And if it's better than that, that means it's significant and we have to care about it. If it's below that, we don't really care about it so much. And we can use this to make a subjective estimate. We can make it a bit more precise by instead saying, what's the probability that my marginal likelihood estimate in t iterations will be above this value? So I can say, I'm going to draw 1 million samples here. What's the probability that I'm going to have a marginal likelihood estimate above that threshold if I draw 1 million samples? And this is something we can work with a bit more directly. So we've got the samples, we can put, say, a kernel density estimator on them, and we can use that. So the probability that the marginal likelihood estimate after t iterations is above the threshold is roughly the probability that we generate one sample above that threshold. As long as t is not sort of infinitely large, if it's large but not too large, if one sample passes the threshold, it's highly likely that the marginal likelihood estimate will be above the threshold. If it's below, it obviously won't be. This can then be estimated through the kernel density estimator itself. So it's 1 minus the probability that all of those samples fall below the threshold, and that's 1 minus the CDF of the true distribution to power t, and we can estimate that CDF using samples. And in fact, we can get surprisingly reasonable estimates from only a small number of samples that can then tell us how reasonable is it that we actually have a marginal likelihood above that threshold. So here we see to the right, it's very unlikely that the true marginal likelihood is above that threshold. The distribution on the log weights collapses quite early and flattens out. We're almost certain that the left child actually does have a marginal likelihood above that threshold, even though our Monte Carlo estimate is 200 orders of magnitude or so off the true value. Putting things back together, this will give us the full traversal target. So our utility of the sampling is going to be 1 over the number of times we've made the choice before. Then we have the first term, we have the exploitation. We have Monte Carlo estimates for what we want to sample from asymptotically. Those are going to be given by the propagation. Then we have this targeted exploration term that we've just shown, where we estimate a subjective thing of, is there a missing mode in this region? And then we also, as final thing, have the optimism boost just to ensure convergence, because maybe both of these estimates went wrong. Okay, so let's now think about splitting. So far I've been looking at sort of bounded spaces and design splits, which is obviously not going to be particularly practical. What we can do though is we can do a reparameterization. So at the back end of your computer, almost everything starts with a uniform random draw and then gets passed through various things before it gives you what you want. So what we're going to do is we're going to split in that reparameterized space before everything gets drawn through. So it's kind of the cumulative distribution space, and we're going to do axis-aligned splits in that space. These splits are then going to imply nonlinear splits in our original space that are aligned with the contours of our proposal. And because it's the proposal, we can always make sure we can do this. The critical thing for this, though, is it's going to allow us to make both easy sampling from this distribution and evaluating its density. So we're doing important sampling, we need to be able to evaluate exactly the density of the proposal, not just up to the normalization constant. And so we have here that the proposal probability of x given x is in some region is just the proposal times an identity in that region over the volume in the reparameterized space. That's a hypercube. So a hyperrectangle, we can calculate that trivially. This means we can do everything easily and ensure the consistency. So now we're knowing how we're going to be splitting. How do we do the refinement step a bit more? So remember, we've traversed the tree, we've selected a leaf node, and now we need to update the tree and update the estimate of that node. What we want to do is we want to add a new split, and we need to choose where we want to put that split. Thankfully, we've already got samples of that node. It's already a leaf node, we already have samples. And the question is, what kind of split do we actually want? Well, we want one that concentrates the mass to as small as area as possible. The more we concentrate the mass, the more we can focus on that area and forget about everything else. So what we can do is we can introduce an entropy metric similar to the one you'll have in decision trees. We can evaluate that based on the samples we already have. So we can just sample at random of various possible splits, and then we can evaluate this metric very cheaply and choose the best one, and that will give us a sensible split. Okay, so let's just recap through the algorithm again. So we've got this tree, and we're learning it online. So the first step we have is we traverse the tree. We go down the tree to choose which node we need to update, where do we need to spend our resources. Once we've chosen that node, we need to refine it. We split it in half, we run inference at each of the new 2 nodes, and that gives us an update estimate. Then we're going to propagate this back up through the tree, so we update all the parent nodes, and that helps guide the next set of traversal samplings and updates our overall estimate for the posterior. Okay, let's have a look a bit more empirically. So the first experiment we're going to look at is a simple Gaussian mixture model, although it's actually quite difficult. So this is an exaggerated variance on each of these. They're actually about 10 to the minus 12 in space, so they're really tiny dots in the middle of there. And what we see on the right is that all 24 modes are very easily captured by the inference tree. They're all of the right size, and it does incredibly well on what is actually a very difficult inference problem. In the middle, we have a more naive thing, where we do inference trees, but we remove that targeted exploration. And here we find it completely misses modes. So we see the target exploration is really important, so that once it sees it might have something, it can keep focusing down to the area and very carefully choose that region. If we just had a uniform exploration, there's no real chance of actually exploring to find one of these modes. We need some exploitativeness in that exploration to actually find them. On the far left, we have kind of a state-of-the-art adaptive importance sampling scheme called PIMAS. And we find here that it finds most, not quite all the modes, but it really struggles to find their respective sizes, and so it gives a pretty poor overall. We can explain this a bit more by looking at the effective sample size for each of them. And we see that both the inference tree methods have very high adaptive sample sizes relative to PIMS in orange at the bottom. So here on the x-axis we've got the number of samples, the y-axis is the log ESS, and we see we've got about 100 times more useful samples with the inference trees than with PIMS. The reason you have this sharp spike at the end is, if you remember back, we had a hyperparameter about how much we explored and how much we exploited, and that hyperparameter is getting changed through the course, and so the kink is when we kind of go into exploit mode and start just churning out samples from the right regions. One of the areas we think inference trees can be particularly exciting though is when we combine them with sequential Monte Carlo. So in sequential Monte Carlo you have a problem that no matter how good your proposal is, you might be very restricted on how good your inference is because of the intermediate targets. So you have a final thing you care about, a smoothing distribution, and you're going to approximate it for a series of filtering distributions. And if those filtering distributions don't match well with the smoothing distribution you care about, it doesn't matter how good your proposal is, you're still not going to do very well. Inference trees actually allow you to circumvent this because they can push through samples through the resampling. So you have this resampling set that always corrects you back to the filtering distribution. But as soon as you start chopping at the space and running that inference there in isolation, those samples get forced through and you can force better look ahead of proposals. So particularly if you've got some variables at the start, say you've got a small number of variables, in this case dynamics variables in an extended Kalman filter, we can be very careful about how we sample those, and we can force those through. So in the results shown here, we have inference trees in blue at the bottom doing very well. In orange and red, we have SMC with different numbers of particles, and this is actually SMC with the theoretically optimal proposal being run. And we see that it's very restricting how well it actually does, because it can't do well in these global parameters where the filtering distribution badly matches the smoothing. The way people usually deal with these cases is not to do pure SMC, but to do some sort of particle MCMC methods like PMMH. So in these, you do sort of MCMC sampling on your global variables, and then you do SMC on the sub-variables. But then you have a problem that you have an MCMC sampler that really struggles to move around the modes. And we see, again, for this problem, that inference trees can define all of the 4 modes separately, whereas if we have the sort of standard approaches here, it gets stuck in one. Okay, let's just recap them things. So the first point we'll be making is about the fact that adaptive inference methods really need to explore and not just exploit. They need to take into account the fact that utility from samples comes in the information they provide for future sampling, not just their direct contributions. And different ways of sampling will give you very different information back. I've then introduced this new class of inference algorithms called inference trees that's loosely based around Monte Carlo tree search. I've shown that we can potentially significantly outperform state-of-the-art adaptive importance sampling of adaptive SMC methods, and I've shown that the targeted exploration in this is really important. And I think this targeted exploration is actually one of the areas that's really most interesting going forward as well. Because if you think about, say, what happens in variational inference, we take all those weights and the log space and we just take their average and use those. But there's a lot more rich information in those than just the Monte Carlo estimate, all the Monte Carlo estimate of their logs. We can actually be really careful about that distribution, and I think there's a lot of things we're missing we can potentially do by looking in more detail at the distribution of the log weights in various systems. Thank you very much for listening. There's a preprint available online I was hoping to get it updated in time for this, but it's probably going to be a bit late. Drop me an email if you've got any questions, or I'm also going to be presenting a poster on something else later today, so feel free to drop by and ask questions. Thank you.
Okay, so we have time for a couple questions.
I was wondering if you could say a bit about how this method scales with the dimensionality of the space that you're trying to sample from?
Yeah, great question. The short answer is we're not totally sure at this point. It doesn't scale too fantastically at the moment, but it's not for the reason you might expect. It seems to actually do relatively well in terms of like the allocational policy as it scales, but the problem you get is if you've got kind of even in the reparameterized space, you still get something that ends up looking a bit like a bell curve, and it doesn't matter how good a box you put around that, that's never going to be that great a proposal. So one of the main things we're looking in is that there's no reason in theory you can't also adapt the underlying inference algorithm. So if you also adapt the underlying inference algorithm, it might have a potential to actually properly scale in dimension, whereas at the moment you're maybe restricted to sort of 10, 20 dimensions. It does, one point here is it does allow it to be a pseudo-marginal approach. So for this problem is actually 1,500 dimensions, but we're only controlling 4 of those that are the ones that really matter. So it's often the case that you only need to very carefully control a few of your variables.
In the sense of only splitting on those 4?
Yeah.
Okay.
Yeah.
I saw another question over there.
Yeah, so many adaptive inference algorithms require for consistency proofs, and some require some diminishing adaptation conditions or similar. Now your method has, I mean, the results are really great, and but it has a lot of choices to make. Right? You made a lot of choices and carefully motivated them. Can you give us an idea? Did you prove, or is it possible to prove consistency for your scheme, or does the adaptation naturally diminish because of this deconstruction?
Yeah, great. So the proof of consistency is independent of all the schemes I've introduced afterwards, provided that you make the maximum depth of the tree fixed. So which can be huge, like you can make it 1 trillion or whatever, but as long as it eventually has a bottom, that will itself stop the adaptation eventually. So the consistency proof is very different to most ones because it's stratified rather than important sampling that's going on. And that kind of makes things easy. The proof is incredibly simple. It's just we have basically a sum of things and those things converge. And the only reason we actually have to bound it is to make sure that they're not an infinite number. I think the proof would actually hold if you kept it going and it was countable, but you want to stop it anyway. So but like from a theoretical perspective, it's very easy, and it's certainly proved in the algorithms that have been run practically later. Or maybe a better thing is the assumptions always hold.
Okay, so let's thank Tom Rainforth again for the great talk.